All right. Is my screen visible?
Yes, sir.
All right. So the last time we were talking about the rigid body kinetics, and we were wanting to decide to derive the equations of motion. We did that first in the frame of reference, which is fixed at center of gravity, and then we wanted to look at how we can transform that to the body fixed coordinates origin, and about which we wanted to do the equations of motion finally. So we started off by application of conservation of linear momentum and conservation of angular momentum, and we introduced some concepts like free vectors, coordinate free vectors, but in essence we were able to derive the expression for the translational motion about the CG and the rotational motion about the center of gravity. Okay, so we looked at the idea that the position vector from the origin of the NED frame to the center of gravity is equal to the position vector from the NED frame to the body fixed coordinates origin plus the body fixed coordinates origin to the center of gravity. So it's a triangle in that vector triangle, and we try to differentiate it and then apply the idea that we can express the derivative in the n frame into the body fixed frame, and that's when we get these quantities. We observed that this quantity was 0 because in the body fixed frame, the location of the center of gravity does not change with time. So only this term is left, giving us that the velocity of the center of gravity in the NED frame is equal to the velocity of the coordinate origin of the body fixed frame with respect to NED frame plus omega cross r, where r is the vector pointing from the center of the origin of the body fixed frame to the center of gravity. And then we applied the Newton's law, and then we tried to use some of these relationships which we had derived in order to put them into the body fixed frame, and then we finally found our matrix form of equations for the translational motions. So this was for the translational modes. And we had that mass times the derivative of the velocity of the center of gravity plus omega cross v. So this turns out to be the skew symmetric matrix with respect to omega pre-multiplied by the velocity of the center of gravity expressed in body fixed frame. This is with respect to the NED frame, but it is expressed in body fixed frame. And that is equal to the force that is applied at the center of gravity. What is missing here is that this is also in body fixed frame. Then we considered the rotational motion about the center of gravity, and there we were looking at the conservation of angular momentum. So the angular momentum here is given by the inertia matrix about the center of gravity times the angular velocity of the body with respect to an axis passing through the center of gravity with respect to the NED frame. And we found that we can actually do the same process, take the derivative in the NED frame and express that, take the derivative in the NED frame and express that in terms of the body fixed frame derivatives. So you start to get an additional term, omega cross Ig times omega mb. So we could put this also into the matrix form, and that yielded us this form for the rotational modes. Where we have the inertia matrix about the center of gravity times the omega dot minus the skew symmetric matrix constructed by this product Ig times omega b times the omega nbb, and that gives us the external force, external moment acting on the body about the center of gravity. Unlike in the linear momentum case where the linear momentum is simply given by mass times the velocity. The angular momentum is not a scalar value, or the angular inertia is not a scalar value. And that inertia matrix about the center of gravity is defined as a 3x3 matrix, and we looked at what are its different terms. So along the diagonal are what we call as the moments of inertia, or the second moments of mass moments of inertia. And the other ones, the off diagonal items, actually are symmetric in nature. So we have only 3 other cross products of inertia, or the products of inertia is what we call these. And their definition is listed here. Notice that in each case we are taking a volume integral and then multiplying by the effective density of that mass, and we are kind of seeing how far the mass is located from the x-axis, from the y-axis, and from the z-axis. And those quantities are allowing us to compute these products of inertia and the second moments of inertia. So putting everything together, we found that the total equations of motion can be expressed as this. So you have some mass matrix times the velocity vector, and this is composed of a 6x1 generalized velocity vector composing of 3 velocities in the linear direction and 3 in the angular directions. And this is the derivative of that. So we have v dot ngb and omega dot nb. And that is added to a centripetal term. So this is the Coriolis matrix. Coriolis and centripetal terms multiplied by the velocity is equal to the external force. Notice that this term, in general, we would have mass times the acceleration is equal to the external force. This part, in essence, is coming about because the B frame is rotating with respect to the N frame. The B frame and the N frame are not, or at least B frame is a non-inertial frame, and that is why you are getting these terms which are coming from the Coriolis and the centripetal accelerations. These matrices themselves can be seen to be pretty regular. So the mass matrix is an identity matrix in the top corner, zeros on the cross diagonals, and then the inertia is there in the bottom 3x3 location. If we look at what is that so-called centripetal acceleration terms, that also can be computed pretty straightforwardly. You see that again, this is a skew-symmetric matrix constructed from omega nb, and bottom half is a skew-symmetric matrix, negative of a skew-symmetric matrix constructed from Ig times omega nb. And this whole matrix is multiplied by the velocity vector to give us the centripetal forces. That is where we were, and we started to just look about how can we convert the so-called equations of motion that we derived here with respect to center of gravity. We want to now derive the equations of motion about the center origin, or the coordinate origin of the B frame. So I want to derive this in the B frame with respect to the coordinate origin, because generally this is a fixed point that I can choose, whereas the center of gravity need not be a fixed point always. So depending on whether we are going on a ballast voyage or are we in a fully loaded condition, the location of the center of gravity may change. And in order to have a consistent way to derive our equations of motion, which are not changing with time, we would prefer to really have them about the coordinate origin. I think this is where we were. Any questions up till here?
Sir, I have a doubt.
Yes.
So, sir, if the origin is not moving, why did we have to compute the equations of motion in the center of gravity frame?
Because they are looking easier. So what I'm going to do is I'm going to now convert those equations about the body fixed origin. The reason is simple. When you have the deriving the equations of motion about the center of gravity, there are certain advantages. So for example, if you look at your mass matrix, you are seeing, where's my pointer? This part and this part are zeros, isn't it?
Yes, sir.
That would not be the case when we derive with respect to the center of or the body fixed frame's origin point as the origin about which we derive the coordinates axis. If we derive the equations of motion about CO, you will find that these terms are non-zero actually. Okay. So in terms of derivation, it is simpler to understand about the center of gravity because you don't have any external factors to think about. But the moment you start to say that I want my equations of motion about any other point, then you have to understand how far is the center of gravity from that point and what effect does it have on the equations of motion. Did that answer your question somewhat?
Yes, sir.
Okay, all right. All right, so our target today is to look at how we can derive those same equations of motion which we have, how can we transform them into about the body fixed frame. So now we already saw that the velocity of the center of gravity with respect to the NED frame expressed in B frame is given as VNBB plus omega NBB cross RBGP, where this is the position vector of the center of gravity with respect to the body fixed frame's origin expressed in the B frame. Omega NB is the angular velocity of the body, and V and BB is the velocity of the origin or velocity of CO, okay, coordinate origin, with respect to the NED frame expressed in B frame. We saw this before. Everybody comfortable with this?
Yes, sir.
Yes.
Okay. All right. So here is where we start to do our first manipulation. So first we interchange the cross product. So we have to introduce a minus sign to account for the change in cross product order. So now I can write the same equation, but in this form, where I have just taken these two terms and flipped the order. Now, after I flip the order, I can write it out in a matrix format. We can see that the velocity of the center of gravity is velocity of the body fixed frame's origin plus a skew-symmetric matrix constructed from RBG, transpose of that times omega NB. Is this making sense?
Yes, sir.
Right? Because this cross product would have been, it would have been S of RBG B times omega NB. And there's a minus sign, so it would have been this. And this minus sign of the skew-symmetric matrix, I am writing that as the skew-symmetric matrix of RBGB transpose. Okay, so that is how I'm getting this last line which you see here. Okay, so now if I want to write out what is my old velocity vector about the center of gravity and I want to relate it to the new velocity vector about the body fixed frame's origin, then I can see actually that the velocity of the translational velocity of the center of gravity is the translational velocity of the center, the body fixed origin CO plus S transpose times omega. So that is how this transformation matrix comes into being. Is that making sense? Yes, no? This equation which we see here, that's just the first row of this matrix equation. Everybody with me so far?
Yes, sir.
Okay.
Yes, sir.
And all I have at the bottom is that the angular velocity is equal to angular velocity, because the angular velocity about the center of gravity or the angular velocity about the body fixed coordinates origin, they would be the same things. They would not be any different. So which is why we have the identity for the second equation. Now I define this matrix which relates the velocities about the center of gravity to the velocities, in fact the other way around, the velocities about the body fixed frame's origin to the velocities about the center of gravity as this matrix H. Okay, I'm just calling it, giving it a name called H. So if I want to find out what is H transpose, all I will be doing is this Q-symmetric matrix will come down to the bottom. Is that making sense? When I take a transpose of this, that Q-symmetric matrix will come down and the transpose will no longer be there. Yes, everybody with me so far?
Yes, sir.
All right. Now what we do is, in order to convert our equations of motion about the CG, which we had derived previously, we pre-multiply those equations of motion by H transpose on both sides. So what are we doing? We are going back to these equations of motion which we had, and I'm saying that I'm going to now take this and pre-multiply by H transpose. Similarly, I'm going to pre-multiply by H transpose on both sides. Is the idea making sense? What am I doing here? Yes?
Yes, sir.
Okay, so the moment I multiply by H transpose, what do I end up with? I have H transpose times the mass matrix expressed about the center of gravity times the velocity vector about the center of gravity. That I am transforming into velocity vector about the body fixed frame's origin. So which is why I have H times this new velocity vector. Tell me if this is clear. Yes, no?
Yes, sir.
Okay, all right. So now, similarly, I'm going to do the second term as well. I have the H transpose times the CRB times CG. This is what existed previously, multiplied by the velocity vector. So instead of the velocity vector about center of gravity, I write it as H times velocity vector about body fixed frame's origin, CO. Okay, and on the right hand side, I simply have H transpose times the forces about the center of gravity. Everybody with me so far? Nothing much. I've just taken those old equations of motion and pre-multiplied on the left hand side, both sides, by H transpose. Yes?
Yes, sir.
All right. Now, this product H transpose times M times H, this product I'm going to call it as MRB. That is my new mass matrix where the coordinate frame is now fixed with respect to the body fixed frame. Okay, this matrix is what I'm calling my new mass matrix, and this matrix is my new Coriolis and centripetal matrix. If I want to expand this out and see what that product actually looks like, this is what I'll see. The mass matrix is pretty straightforward. You have the mass times the identity matrix, 3 cross 3 identity matrix. And the right top, here you have minus m times the skew symmetric matrix times RBG. On the bottom you have m times the skew symmetric matrix times RBG. And here you have IG minus ms square RBG. Okay, this is what you come up with when you perform this multiplication of H transpose times H the mass matrix times H. That skew symmetric matrix due to RBG is basically coming from the H matrix. Okay, so this is what you will end up with. Is that making sense?
Yes.
See, the only difference here is previously these matrices, these 3 cross 3 sub-matrices were zeros when we had the mass matrix expressed about the center of gravity, isn't it?
Yes, sir.
It still turns out that if I choose my coordinate origin to coincide with, if I choose that CO will coincide with CG, then RBG will simply be zeros, right?
Yes, sir.
If I put that in, I see that I get back my original matrix, which was about the center of gravity. Correct?
Yes, sir.
Yes, sir.
All right. And what you see here is that the inertia as if has changed. So the inertia about an axis due to the about an axis passing through the body fixed frame's origin will be different from the inertia which you saw from the about an axis passing through the center of gravity, and the difference is given by this. This is nothing but a sort of parallel axis theorem. Which is basically telling you that the I about the body fixed frame about the origin of BCS is I about the G minus RBGB cross RBGB cross omega NB. That's what this is telling you. And I think there was a confusion that some of you asked me why the minus sign here. And in fact, if you express this cross product out and you absorb that minus into your cross product orders, you'll see that this actually does come out to be. So suppose I chose, let's say that okay, so I have IG minus M times S of RBGB squared, right? And this whole thing gets multiplied by omega NBB, and that will give me the so-called inertia times the angular velocity. So if I want to see what this fellow is doing here, okay, so I have M times RBGB cross RBG E cross omega NB B, negative of that, right? Let us say, for example, I consider the case where the angular velocity of the ship, I'm purely considering about the X, Y is pointing out and Z is pointing down, let's say. Okay, and let us say for argument's sake that the only angular velocity of the body is purely due to the about the y-axis. So where is the y-axis pointing here?
Towards us.
It is pointing towards us, right? And a positive orientation of that means how is the body rotating? The rotation clockwise or anti-clockwise?
Anti-clockwise.
The rotation is like this, right? Anti-clockwise. Correct. Now, let's say, so in that case, what is my omega NBP? What does this vector look like? What will be the first term?
0.
0. Let's say the second term is the angular speed is omega. The third term will be
0.
0. So this is what I'll get, right? And let us say that we are looking at a ship-shaped section. So RBG will be, let us say, some xg. Yg will be 0 because symmetric about the center line times zg. All right. Now, can you compute this entire thing? Minus m times rbg cross omega nb. Let's try to do that. I, j, and k. And then I have xg, 0, zg, 0, omega, 0. So this will be only the product rbg b cross omega nb b. What does this turn out to be? Xg into k minus zg into I. Is that making sense? Yes, no?
Yes, sir.
Okay. All right. Now I am taking a cross product of this with RBG. So I take I, J, K. I have XG, 0, ZG. And then I have minus omega ZG, 0, omega XG. Right? So this is R cross omega. What will this be?
Minus j times sj.
Yeah, go ahead.
Minus j times omega xg square plus omega zg square.
Times J.
Okay.
Right? Now, and I'm taking a minus of this entire thing, right? Minus m times this whole thing. So that entire product will now become m omega square xg square plus zg square, which means that if my coordinate point, so let me draw this here, this is xb, this is zb, and the center of gravity is located at some point here, such that this is xg and this is zg. Okay, what it is doing, it is adding more moment of inertia than what I had with respect to center of gravity. And how much am I adding? M omega square r square. Okay, so I'm basically computing the distance of the new axis from the current axis, which is x square plus z square, square root of that, and I'm doing m omega square r square, where r is xg square plus zg square. So now, does it make sense why that minus sign is important? If it was not there, we would actually be ending up with a negative value, which would be incorrect, correct? Is that making sense for everyone?
Sir,
Yes.
sir, how is it omega square?
Sorry, it is omega, my bad. It should be m omega r square, correct. My mistake, m omega r square. Is that making sense for everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fantastic. So let's come back here.
Sir,
Then we have,
Sir, in this MRB matrix, this IGB, so this is the moment of inertia matrix about an axis passing through G,
correct.
and that B, like it is a matrix, right? So
Correct. So IBB also will be a matrix. This will be the inertia of the body about an axis passing through B.
but this superscript, like in for a matrix, superscript, like what does it signify?
It only means that I'm expressing it in respect to the B frame. I'm just saying that this inertia matrix is being expressed with respect to the B frame. If I express that with respect to the N frame, then it will be time varying in nature. So think of it like this. I don't know if you guys can see me. So
No,
let's,
like I'm confused in the sense, like for a vector, like it's okay if a vector is expressed in some frame, yes, but for a matrix, in some frame.
correct. So inertia also we are exactly expressing it with respect to some frame of reference. You imagine that, let's say that my NED frame is here, okay, wherever my hand is, right hand is,
Okay,
okay, and my ship is here, okay.
okay, yes,
If I want to compute the inertia with respect to this, it will really depend on how much distance it is at, right? How far is the center of gravity from the NED frame?
okay,
And as it keeps moving, my inertia matrix will be keeping on changing.
because the distance between NAD and our ship, it changes.
Correct. So therefore, if I wanted to express that inertia with respect to the center of gravity, let us say, about the NED frame, then this would be time varying in nature. But I want to express it in body fixed frame so that it is no longer time varying in nature.
Yeah, and also one thing, can you go in that MRB expression?
Yes.
So initially we designed all the equation of motion with respect to the center of gravity, and then we are doing the same exercise for the body fixed origin.
Correct. We are kind of transforming those equations about center of gravity to be expressed about some other point, which is going to be CO in our case, coordinate origin.
Yeah. So the main reason for this was that the center of gravity is not maybe a fixed point. It may change during our travel, like ship travels.
So, and we may not know its exact location. So let us say that I have a container ship, for example. Okay.
Yes.
And then I go to the port of Los Angeles. Suddenly I take off some containers, I put on some new containers. I don't know where my new center of gravity is.
Yes.
Right? I may have an estimate about it, but I won't know for precisely. But I can fix the value of CO or the coordinate origin precisely. I can precisely fix it wherever I want.
Yes. Yes. But here still we are calculating this IG. That is about an axis passing through the center of gravity. But
Correct.
that G might change, right? That's what is my question.
Correct. This IG is the moment of inertia about a point passing through the center of gravity. Correct.
But that might change, right? So
Correct. Usually that is not what we want. Usually this is what we want to know.
yeah, but that is calculated using this IG, no?
No. So if I want to actually, let us say, let's take, for example, our own ASV. Okay.
Okay.
If I wanted to find out what is the inertia of our ASV model, I would actually take the entire model and swing it on a swing bench. Right? That would allow me to actually compute this fellow. This is what I calculate.
Okay, directly we calculate this IBB.
Correct. This is what we calculate.
Yeah.
And from there, actually, I have to figure out where the center of gravity is using an inclining experiment to find out what this thing is.
Okay.
And then compute what is the inertia matrix about the center of gravity.
Yes.
Okay. Otherwise, what would I have to do if I really wanted to find IBG? I would have to somehow ensure that I turn the model precisely about an axis passing through the center of gravity even before I knew where it was. Highly improbable.
Yes.
Right? So usually this is calculated first. It's usually we have more control over this thing.
So, like, can you explain it how that IBB is calculated?
Correct. So what you generally do, or what is generally done, is that you have a table. Okay, my drawing is really pathetic already, and to draw on this is becoming more pathetic. Right. I'll try my best. Okay, and then let's say that I have a frame which I put up. Okay, and this is the axis about which I am rotating it. Okay, so I'm giving some small oscillation, let's say. And on this bench, I usually place my boat. This would be the right approach to calculate the inertia. Okay.
Okay.
Now I take it, I swing it, and I observe what is the period that I get.
Okay.
Natural period that I get. It's like a pendulum exercise.
Oh, yeah.
So I can then find out basically from this, knowing how far the distances are from here to the base, I can compute what is the moment of inertia of this boat about an axis which is passing like this through it.
Yes.
Right. Similarly, I can turn it around and I can do it for the yaw as well.
Yeah.
Right. But if I wanted to do it about roll, I have to get a little bit more innovative. I have to turn the model somehow by 90 degrees. My boat should somehow be sitting like this. In that case, when I turn it this way and this way, I'll get the roll motion. Okay. So that's typically how you get the moments of inertia. There is another way too, which is called the shake table, which means that you have a full-fledged table which is mounted from another platform with respect to springs. Okay, my drawing of spring is really bad, but that's okay. Right? And then I simply bring this, put the boat on here, and I just try to shake it in all different directions, up, down, sideways, what you call. So I give translations in these directions, translations in these directions, maybe translations in the direction perpendicular to the plane, and then I also do rotations. I twist it in this direction, I twist it about this direction, and I twist it about this direction. So I get all 6 moments of inertia at once.
Okay.
Because I know what these springs are precisely, I know what their stiffness is, so I'm measuring basically the time period again, and from that time period, I know that omega is equal to square root k by m, right? Typically, where this is changing definitely. Instead of mass, now we have the inertia in place here. But since I know omega and I know what k is precisely, I can find out what the moment of inertia are.
Yes, sir.
Very good question. All right. A similar expression, an expanded expression for the centripetal matrix can also be seen, and I leave it as an exercise for you guys to see that if you actually multiply H transpose times C times H, you should get something like this. Okay, so I'll leave that as an exercise. A good way to try that out would be to use symbolic MATLAB. That is be a symbolic toolbox in MATLAB to get these sort of expressions verified. That would be the right way, rather than deriving them manually. Although you could derive them manually, but it will be pretty tedious. Okay, so if I now want to look at what is the translational motions or the equation of motion about the coordinate origin for the translational modes, then what do? I go back to this so-called new equation of motion I got by pre-multiplying by H transpose and converting the velocity into the body fixed frame. I take the first three rows of these three matrices multiplied by the vectors, and that will give me the equations of motion. So I'm looking as if I'm looking at the top half of this matrix multiplication. Okay, is that making sense?
Yes, sir.
Right.
Yes.
So for example, if I'm looking at the MRB, I'm more interested in the top part. That would tell me what is happening with the translational modes. So I have m times the velocity vector derivative. So that is what you see here, m times the derivative. Notice here that this is an identity matrix, so it's not really making much difference. Minus m times s rbg minus m times s rbg times omega dot. Is that making sense? Are the first two terms making sense? This mass matrix is being multiplied basically by the velocity vectors derivative, right? B and B dot omega and B dot. So the second term gets multiplied by this. So which is why we have minus ms rbg minus m s rbg times omega dot. Then we have the next term, which is coming from the top half of this CRB matrix, m times s omega n b, m times s omega n b times the velocity vector minus, I have this entire thing, s omega n b s rbg times omega n b. Is this making sense? The second part gets multiplied by the omega value. Is that making sense? This term gets multiplied by V NBB, and this term gets multiplied by omega NBB. And that's all. I'm collecting the terms.
Yes, sir.
And that would be giving me the force vector about the body fixed frame. In fact, there is a mistake here. This is a mistake. This is a small mistake here. This thing is not FG. This is FB. It should be FBB. Okay, where this FBB is nothing but where I took that H matrix, right? H transpose times FGB. So if I look at that H transpose, it is I3 times FGB plus 0 times MGB. Is this making sense? See, this H matrix is there, no? The H transpose times this vector is what I am considering, right? Again, I have to consider the top half of this.
Okay.
Right? So I have I3 times FGB plus 0 times MGB. Everybody with me?
Yes, sir.
But then it came out FGB only, right?
It actually came out to be FGB only. Right? Yeah.
Yes. Yesterday in the book, like we were reading, and they somewhere it is written that FGB is equal to FBB.
Correct.
So,
it will be, right? Because if I am considering a ship, let's say, and I know the force acting on it, external force acting on it, to be FGB, about the center of gravity. Even if I consider a transformation to CO, the force will still be the same. Right? These both will have to be the same. Only the moment due to them will have to be accounted for. It's only in the moment I can't say that MdB will be equal to MdG. This will not be the case.
yeah.
Right? But the force will have to be the same. So therefore, that's why you're kind of seeing that the force comes out to be the same by this multiplication which you did, H transpose times this matrix. In fact, if you look at what happens to the moment, you can kind of already guess that, right? That here, when I do the moment, and I am looking at the bottom half on the bottom here, I'll have SRBGB, which is the term here, right? Multiplied by FGB plus I3, which is identity matrix, times MGB. So it will simply become MGB. And this thing is actually equal to MBB. So if I actually put this in the so-called vector notation, what do I get? MBB is equal to MGB plus RBG cross FBG. So because when I had about the center of gravity, the moment was MGB. When I want to compute the moment about the coordinate origin, MBB, they will not be the same. In fact, MBB will be MBG plus an additional component, which will be the R cross the force vector here. That making sense? Is that making sense? When I make a transformation, the moment changes, isn't it?
Yes, sir.
Yes, sir. Yes.
Right? So that change in moment is nothing but the old moment plus R cross F. Because the force was acting at the center of gravity, now that will contribute an extra moment which will be denoted by R cross F. And that is what we are seeing here also. When we do this multiplication H transpose this, we're actually getting that idea that it is nothing but R cross F. Everybody with me so far?
Yes, sir.
Okay, so I'm coming down here and looking back at my equations. So as Vallabh rightly pointed out, it does actually come out to be FBG. So, and FBG is equal to FBB. All right. So therefore, what our equation of motion now becomes is slightly, I'm going to make some small changes here. so that I can express it in a neater format. So let's see what I do here. I take this second term here, this one. Okay. Can you see that I can write this as this? Are the two equivalent? They are equivalent, right? Because this basically represents minus r cross omega dot, and this one simply represents omega dot cross r. They both are the same, right? Okay, now the second term I'm keeping is this third term I'm keeping it as is, and the last term also I'm making a change. See, this last term, what does it represent? This represents omega cross minus of omega cross r cross omega. Correct?
Yes, sir.
Okay. What does this last term here represent? Omega cross r. Yes.
Yes, sir.
Right? It is easy to see actually that these two are equivalent. I will leave it as an exercise. All you have to take is that this minus sign gets absorbed into the inside cross product. It becomes omega cross r. But now with a positive sign. Okay.
Yes, sir.
Right. So I have now written this down in this format. So in the vector form, if I wanted to convert this matrix form into the vector form, I can now write mass times the velocity dot plus omega dot cross r plus omega cross v plus omega cross r is equal to f. So that becomes our translational equation of motion when we are expressing this about the center of, about the what? Body fixed frames origin. When we want to express this about the body fixed frames origin, that is what we get. The rotational matrix is again the same idea, and I think we already talked about this, that IBB is IBG minus MS of RBG square. We already saw this, and we also actually considered a 2D example to make sure that it's making sense to us, that this is actually nothing but the parallel axis theorem. That's the parallel axis theorem. Okay, now, okay, in order to continue further, do you guys have any class right now?
No, sir.
If you don't have, I will just try to finish this part because it will be very difficult to pick it up back from here. Now that we have been discussing, we'll keep forward just to finish off the equations of motion, and then we'll call it quits. Maybe 10 minutes at max. Okay, so now we see that the MRB matrix, which we were finding out by doing that H transpose MRB about the center of gravity times H, that thing was MRB, right? And if I look at the bottom right half of that matrix, or the submatrix, the 3x3 submatrix of it, which is in the bottom right half, I can see that that thing was nothing but Ig minus Ms square. So which is nothing but the new moment of inertia about the body fixed frame. We already saw this, just to refresh your memory. This is what we saw, right? And that thing is what I'm representing as the body fixed frames inertia. Inertia of the body about a coordinate axis, which is passing through the body fixed frames origin, rather than about the center of gravity. Yes, We just saw this, isn't it?
Yes, sir.
Correct. Okay. Now, that part is pretty straightforward. Now, we can also transform some linear algebra is required to transform this Coriolis matrix, the bottom right half of it, in order to express it in a neater format. So what was it originally? This CRB22, which is this matrix bottom right half, which you see has two terms, right? M of S RBG, S of omega, S of R, minus S of IG times omega. This is what we had here. That term we are going to simplify it a little bit so that it is a little bit better expressible when we write down our equations of motion about the body fixed frame. Notice that we are not changing anything. The equations are still valid in the current form that you see here. Only thing is that we want to make it a little bit neater, or we want to use linear algebra to simplify a little bit of it. So that instead of expressing this expression in terms of IG, I would also like this expression to be in terms of IB. So in order to do that, I have to do some little bit of linear algebra manipulation. And that's what we will see how we are doing it. Everybody with me, what we are doing? We want to express this in terms of IBB. Yes, no? Not clear, not making sense?
Why IBB?
Because we are writing our equations of motion about the body fixed frame, right? So we would like to express it also in terms of the inertia matrix about the body fixed frame.
No, I mean you said that this CRB part we will be trying to write in terms of IBB, right?
Correct. So because you see the MRP part, it is very straightforward. That 2 term is actually nothing but directly equal to IBB. So it was a very simple process for us to express that in terms of the body fixed frame's inertia. But that CRB terms 2 term, or the bottom right half of the term, it is still expressed in terms of IGB, right? I would like to express that in also in terms of IBB.
Okay.
And that's what I'm trying to do here. So all I have done here is gotten the same expression from what we had here when we derived this CRB, this 2 term, this bottom right half of the term. That is what we want to see how I can express that in terms of IBB. So this is our starting point. The same expression I've written it here, and now we'll start the manipulation. What we'll do is we'll first take it out into the vector form. So I can clearly see that this will be R cross omega cross R cross omega. Can you see this? These 4 matrices, the 3 matrices times the vector will actually become, the first one will be R cross omega, that is here, multiplied by cross product with omega, further taken a cross product with R. Is that making sense, right? Okay, and the bottom one is nothing but IGB omega cross omega. Correct? This term.
Yes,
Cross product with this. All right.
Yes, sir.
Now, this top term is what I want to simplify a little bit. So in order to make it a little bit more easier to have a convention or to write it down, I'm going to represent this RBG vector as A and omega vector as B. So can I say that this product is nothing but A cross B cross A cross B?
okay.
If I make the substitution, A vector is R and B vector is omega, then this above expression which you see here is nothing but A cross B cross A cross B.
Yeah. Yes. That's
Okay. Now I want to simplify this cross product. In order to make a simplification, we will use what is called as the Jacobi identity, which states that for any three vectors A, B, and C, A cross B cross C plus B cross C cross A plus C cross A cross B is equal to 0. And this basically comes from your linear algebra. And vector spaces. Or at least I would hope that a part of this was covered in your mathematics course, which was to begin with. You may not remember it quite clearly, and neither did I. So you might want to Google this out and see what that is. But the identity states that any three vectors, if I take a vector cross products in the order, and I take this order and sum them up, they should turn out to be 0. Is everybody with me so far?
yes, sir.
Yes, sir.
So this Jacobi identity is what we are going to use to simplify our expression for this. And how do I do that? I will substitute C is equal to A cross B into this expression. So if I put C equal to A cross B, can you clearly tell me which one term will become 0 here between these three?
The third term, sir.
The third term will become 0, right? A cross B times A cross B. Because if I take a cross product of the vector with itself, we know that that will be 0. Is everybody with me?
Yes, sir.
Okay, so only thing which will be left is here. So this term, the first term is what I have in the beginning, and that will be equal to now. So I can say that this thing is equal to minus B cross A cross B cross A, which is nothing but I'm substituting C equal to A cross B and taking it to the other side. Is this making sense?
Yes, sir.
Yes, sir.
Okay, so this cross product which I had to begin with, I'll now rewrite it in this manner. Okay, so by doing that, this is what I'll get. Minus B cross A cross B cross A. This is what I'll get. Now, that minus sign I can absorb in so as to change the order of the cross product. So I'm taking A cross B cross A cross B. So I'm just shifting B to the other side and absorbing that minus sign into it. Everybody with me so far? How I got here?
Yes.
Okay. Then what am I doing? I'm pulling out another minus sign by changing this order of cross product again here. So that's why a minus sign comes out and I have A cross B cross B.
Yes.
Yes. So now if I wanted to express this thing in terms of the matrix form, what would it become? Will it be the same as what I have shown here?
Yes, sir.
Will be the same, correct? Because this product is A cross B, so that is nothing but represented by this. And then I take a skew symmetric matrix due to that and pre-multiply it by B. Everybody with me so far? Everybody with me so far?
Yes, sir.
Yes, sir.
Okay. Now, this skew-symmetric matrix SA, SB, SA times B, which was originally what was here, right? This is what I had. SA, SB, SA times B. Now it will be rewritten in terms of this new version which I found out through that manipulation. So I can in fact write that CRB22 term as M times S of S square R times omega n B multiplied by omega n. Okay, so instead of this product here, whatever I had here, I'm replacing that with my new expression. Everybody still with me?
Yes.
Yes, sir.
Okay, now you see, if I take, can I write this thing as the two terms are being post multiplied by omega nb, so I can take a common, and I'm forming a skew-symmetric matrix due to this vector, and then forming a skew-symmetric matrix due to this vector. I can combine them both, and I can say that I'm forming a skew-symmetric matrix due to the first vector times omega nb, which is here, and the second one is S square R times omega nb. I'm just taking it into a common factor. Tell me this part is making sense to you. Is this making sense?
Yes, sir.
For everyone?
Yes, sir. I think I got it. Yeah.
Everybody?
Yes, sir.
So we put one more minus sign outside.
We put one
Oh,
more.
so this IGB. Okay, yeah.
Yeah, because there was a minus sign here to begin with, no? So that we are keeping it here. So since this term became positive, I had to pull another minus sign to account for it. That's all.
Yeah.
Now, if you observe this inside thing, Ig minus ms square r, that looks familiar. We have seen it somewhere, isn't it? What is that?
IBB.
Yes, sir. It's IBB.
That is IBB. So instead of now having Ig, I can now replace that with IBB, and then my simplified expression now becomes this. Okay, now using this so-called simplified expressions for MRB22 and CRB22, the equations of motion for the rotational modes are given by, we can put them all back up. Okay, so let me back up there and show where we were. So if now we are talking about the bottom half of this matrices, because we are talking about the rotational motion, correct? So this term will be IBB times omega dot plus MS RBG times V dot. Is that making sense?
Yes, sir.
Okay, so let us see whether we have that there or not. So we have IBB times omega dot, that is the first thing, plus M times S of RBG times V dot.
Yes.
So far so good?
Yes.
Now, we are again going back, and we are now going to take a look at that CRB matrix, again bottom half. We have this term which is now simplified. What does this term become? It now simply becomes S of IBB times omega NB. right? So that will be multiplied by omega n dB, and this term here will be multiplied by V n dB. Correct? That is what we should have.
Yes.
Okay, so R omega V. Let's see. We have R omega V, and then we have S times I omega B IBB times this. Wait a minute. Correct. We have, and here I have made a transformation. So this term ideally should have been minus S of IBB times omega NBB times omega NBB. Correct? This is what it should have been from what we saw above.
Yes.
So which is nothing but IBB omega NB cross omega NB. That means this is nothing but omega NBB cross IBB cross times omega NB. So I'm changing the order of cross product in order to absorb that minus sign. Right? And now that can continuously be written as S of omega NB times IBB times omega NB, which is the same as what you saw here.
Yes, sir.
Is that making sense? Fantastic. Okay. Now, on the right hand side, we have MBB as the output, which is MBG plus S times FG. We already saw that this is the case, which is basically representing MG plus RBG cross FBG. Correct?
Yes, sir.
Yes, sir.
So in the vector form, if I want to express this entire equation of motion in the vector form, I can simply say that this will be IBB times omega NB dot, IBB times omega NB dot. This term will be, I'll first consider this fellow. That will be omega NB cross IB times omega NB. Omega NB cross IB times omega NB, which is what we saw here, no? Okay, second term done. Then we go back to this term, R cross V dot, R cross V dot. And then finally we have our last term, which is R cross omega cross V, R cross omega cross V. And that must be equal to NBV. Is that making sense?
Yes, sir.
Yes, sir.
So if I want to put everything together, then I can write down my consolidated equations of motion as MRB times V dot plus CRB times V is equal to tau RB, where this MRB is what we saw before. Now we have simplified these things with respect to IBB. So notice that here we will no longer find IBG to be there anywhere. We are expressing always in terms of IBB. Similarly, the CRB matrix also we are expressing in terms of IBB. That is why we went through this much effort to express both these matrices purely in terms of the inertia matrix with respect to the body fixed frame. That was the primary idea. So in this case, we can now see that this generalized vector V is nothing but VNB and omega NB concatenated together. Or in other words, if I want to see in the body fixed frame, this would be U, V, W, P, Q, and R. And similarly, the force here would be X, Y, Z, K, M, N transpose. Okay, notice that all these quantities are now expressed in the body fixed frame about the axis passing through the body fixed frame's origin. So no longer we are talking about things with respect to the center of gravity, but rather we are talking about things with respect to the body fixed frame, and we are taking moments about the origin of the body fixed frame. Is that making sense?
Yes, sir.
Okay, so we have not really done much here. We have only taken those terms in MRB and CRB which were not having IBB directly in them, and we have simplified it such that IBB is now there, and we are not talking about IBG because, as we had a previous discussion, we typically like to find out IBB first before we can find out IBG anyway. That is a much more harder quantity to find out. Okay, so I'm going to stop right here. Also, the expressions for if I expand this completely out are also given in our notes. So you can take a look. Usually we will not be going back to these forms. It is just for completeness that it is mentioned here. So if we expand all the forms out, the matrix multiplication completely out, this is what you should get out of it. Now, the last thing which I want to cover before I wrap up today is that you will notice that this MRP matrix is a symmetric matrix. Okay, so if you go back and see your MRB matrix, it is a symmetric matrix. Okay, notice that this minus is not there here because the skew symmetric matrix, when flipped, because of that skew symmetric matrix property, S of RBGB will be equal to minus of S of B transpose. Because of that property, you will see that this matrix is actually symmetric in nature. Is everybody with me on that?
Yes, sir.
Okay, so since that matrix is symmetric, we will also find that that matrix is positive definite. Notice the convention here that when I write that the matrix is greater than 0, doesn't mean that each element in the matrix is greater than 0. Here what it means is that the matrix is positive definite. So which means that if I chose some vector x, any vector x, and I took a transpose of that multiplied by the matrix that I am talking about times the matrix, the vector x, okay, this thing will always be greater than 0 no matter what x I choose, as long as x is not chosen all as zeros. That's what this means. Okay, that is what is as a positive definite matrix. Yes.
Sir, we can take imaginary terms too for x.
No, real. We're talking about everything about real terms so far.
Yes.
Okay. And you'll also observe that the representation for MRB, which we have found, is unique for a rigid body, which means that the representation which we have seen here for MRB, this representation right here, is unique. However, the same is not true for CRB. The representation for CRB is not unique. There could be multiple different representations in which I can write down CRB and still it represents the same equations. Now we'll talk about that in the next class. So for now, we'll leave it at here that MRB is unique, but CRB is not unique, and we'll look at a few other representations in the in the coming lecture. So that is all for today. We will stop right here. Any questions before I close the recording? questions? In that case, let me stop recording here.